Hello, welcome back. I want to housekeeping. We'll talk about a few things. First off, I'm going to create a video going over the star problems that we did last week. It seemed like there were some questions on those, and so I'm going to make it. So if you have not seen that other video, go back and watch it, and please check your answers. This Part 4 is our last section of our astrophysics unit, and it is the last of the new information for the school year. Last PowerPoint, last presentation. We're going to spend this week talking about the solar system and other planetary systems. Next week, we're going to take a test on astrophysics, and I will send out some details on that later. So there will be a test next week, by the end of next week. And then we're gonna have 1 week to review for the final exam, and then the final. So the final is going to be multiple choice, and it's going to be on everything from the whole semester. So it's going to be covering our unit on energy, potential energy, kinetic energy. We built trebuchets, so all that stuff is going to be on there. The wave stuff is going to be on there, and then this astrophysics part at the end is going to be on there. So that's it. We have this week solar system, next week wave test, following week review for the final, and then the final. So, and the last thing I want to talk about is please watch the videos inside the presentation, because some of the answers to the questions are going to be in the videos. So that's just my way of making sure that you watch those videos. So so let's go through it. Here we go. The solar system. So the solar system, it's the sun, and it's basically everything around the sun. So our solar system is the sun. It's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. It's all the planets. It's even Pluto. It's all the comets, all the asteroids. Everything around our sun is in our solar system. So how did it form? There was a nebula from a previous supernova. So a star, before our sun was even here, before anything was here, there was a star that exploded, supernova exploded, and all those elements from the supernova were kind of floating around in space. So all that star debris, right, from the explosion was kind of just floating off in space. And eventually, gravity pulled all that dust and all that star stuff from the explosion. It kind of pulled it back together. And 99% of it went into the sun. So 99.9% of the mass in the solar system is in the sun. And the other 0.1% makes up everything else. So it makes up all the planets, it makes up all the comets, all the asteroids in our solar system. So all the mass from Mercury, Venus, Earth, Mars, Jupiter, all the planets, all the comets, that's only 0.1%. The other 99.9% is in the sun. So the sun is huge, 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 very massive, which is why everything's going around the sun. It's just that much more massive. So the 0.1% of matter swirled around in what is called a protoplanetary disk. So it's just kind of like this flat disk of dust and gas that's still swirling around the sun. And eventually, gravity pulls them together into small bits of rock, which are called planetesimals. And these are gravitationally attracted to each other, and they form larger rocks and larger rocks and larger rocks, and eventually they form the planets. And then, if you look at the solar system, we have the sun, and then you have Mercury, which is a rock planet, Venus, rock planet, Earth, rock planet, Mars, rock planet, and then you have Jupiter, which is a gas giant. So Jupiter doesn't have a surface. It's just a big ball of gas. And the same is true with Saturn and Uranus and Neptune. So those four at the end, those gas giants, they're big balls of gas. You can't actually walk on them. There's no surface to walk on. So why are the planets close to the sun rocky and the planets far away gaseous? The reason is because the sun has solar winds. And so the sun is throwing off all this energy, right? And when it throws off this energy, it literally blew away the gases that were around the inner planets. So that's why Mercury, Venus, Earth, and Mars are rocks. We do have a little bit of gas in our atmosphere, but we're not these big giant balls of gas because the solar winds blew all those away. But the farther out, the farther out planets, Jupiter, Saturn, Uranus, and Neptune, those are gassy because the winds didn't blow away the gases. All right, so here's one of the videos. It kind of talks about how the solar system was formed, and like I said, please watch these videos because some of the questions are not in the slides, they're in the videos because I want you guys to watch the videos. So take a look at this one. I try to pick videos that aren't very long, so take a look. So the asteroid belt. Located between Mars and Jupiter is the asteroid belt, and the asteroid belt contains millions of asteroids, and some of them are like dust particles, very tiny, and some are 250 miles in diameter. Not all asteroids live in the asteroid belt, but most of them do. So we do know that some asteroids are flying around the solar system. We've seen some hit Jupiter, some have hit Earth, some have hit the moon. We have evidence of them hitting the moon and the Earth. We have like these big craters, right, on the moon and the Earth from when asteroids have hit. So all of them aren't in the belt, but most of them are. Contrary to movies, there is a lot of space between asteroids. So it's not like the movies where you have all these rocks and you're like weaving in and out of the rocks. You would actually have to aim to try to hit one. So there's a lot of space between them. It's just this area has a lot of them, but space still has a lot of space to it. So here's a picture. So we have Earth's here, Mars is here, and then the asteroid belt lies in between Mars and Saturn. And like I said, this looks like it's highly crammed in all these rocks together. It's not true. They're really spread out, but there are millions of them there. So here's the video once again talking about the asteroid belt. I think it's only a couple minutes long. So take a look. So Jupiter's role. So Jupiter was actually instrumental in the formation of our solar system. And the reason is because it is so massive. Because it's so large, there's so much gravity from Jupiter that it affects a lot of things. And one thing is it helped, it's the reason the asteroid belt is here. This video kind of goes on to talk about why is Mars small and Jupiter is really large. So the reason that Mars is small and Jupiter is large is because Jupiter kind of siphoned off some of the nebula, the gas and the dust from the nebula that should have gone to Mars, and it pulled it into Jupiter, made Jupiter extra large. And you had kind of like this tug of war between the gravity of the sun and the gravity of Jupiter, and it kind of, these asteroids didn't form into Mars, they didn't form into Jupiter. So it's kind of like just leftover rock that should have gone one way or the other, and it just kind of didn't go either. It just kind of stayed there in the middle. Jupiter also kind of acts as our, it's kind of like our big brother. It's kind of like a vacuum cleaner. If any rogue comet or asteroid is in our solar system, because Jupiter is so large, it does a good job of either scooping it up, sucking it up like a container, and the asteroid or the comet will hit Jupiter, or it will kind of kick it out. The gravity will kind of swing the debris away. So it kind of works as like a cleaning object. It's so large, its gravity really kind of cleans out the solar system space stuff. So if anything rogue comes flying through here, Jupiter's kind of like the bouncer. Just like make sure that too many things don't get by. Why do planets have rings? So rings are materials that should have formed a moon. So all these rocks that are in the ring, and the rings are made of rocks and dust, should have been a moon. However, they're too close to the planet to form a moon, and the gravity just wouldn't let those rocks form, and like a big object there. And so we get rings. And Saturn is most known for its rings. Little piece of trivia, the rings of Saturn are actually vanishing. They're slowly going away. But Saturn is not the only one with rings. Jupiter, Saturn, Neptune, Uranus, they all have rings around them. So pretty much the four gas giants, four gas giants, all have rings. They're just not as prominent as Saturn's. The Kuiper Belt. So past Neptune, the last planet, is the Kuiper Belt. And the Kuiper Belt is a collection of rocky and icy material in orbit beyond Neptune. So it's kind of like the asteroid belt, but instead of being between Mars and Jupiter, it's past Neptune. And the Kuiper Belt is where Pluto's at. So Pluto's out there. There are other big objects out there. And, so watch this video and kind of talk about the Kuiper Belt. And then finally, the last thing that's out in the solar system is the Oort cloud. And the Oort cloud is, you can kind of see it here. It's kind of like this cloud of very icy objects, and it's on the very outside of the solar system. And we think the Kuiper Belt and the Oort cloud, we think this is where a lot of the comets come from. They come from far away outside areas, which is why they're kind of like icy, dirty snowballs. So a couple more videos talking about the Oort cloud here and here. So whenever we see the solar system, it's usually not in scale. And so here's two videos showing the scale of the solar system. This one's from Mark Roper. If you're not familiar with him, he's the one that did the glitter bomb, where he had people stealing his packages, his Amazon packages on his doorstep. So he made a glitter bomb that people would steal, and then it would explode, and he'd record it. So he's using drone footage and using putting everything to size and distance-wise and object size. So you can kind of see how far away the planets really are and how big they are compared to the sun. This video is kind of the same thing. It shows the actual size and spacing of the planets. Obviously, the planets aren't this close, but this one does show this still image here does show the size. And we have all these moons of the planets, and the moons of the planets, you can actually see it compared to like the Earth or Mars. Like some of these moons are as large as Mars. So, and it also shows the distances as well. So take a look at those two videos. There's really not, the only thing I really want you to get from these two videos is that everything is really, everything is very spread far apart, and everything is really small compared to the sun. So just those two things. Whenever you're looking at a map or a model, usually they don't get the sizes right. It's not to scale. So I think both of these videos do a good job showing that. So Recently, we have discovered lots of extrasolar planets, also known as exoplanets. These are planets that are orbiting other stars other than the sun. And so, as of this month, 4,260 have been detected. That is a whole lot of them. And they range from uh, gas giants like Jupiter to rocky planets like Earth to huge, large rocky planets. And some of them have just crazy weather, and some of them are made of like diamond because the carbon was squished so tight together. And there's all kinds of crazy exoplanets out there. There are many detection methods we use to find these planets. The two main ones I want you guys to think about is transit and radial velocity. Transit, what they do is they look at the light from the star, and you can see how much light the star is making. And when the planet goes right in front of the star, it blocks a little tiny bit of light. And we can detect that little bit less light. And using that, we can determine the size of the planet, and that there's a planet there that's actually blocking some of the light. And we're talking about just a small bit of less light. And it's periodic because the planet is orbiting. So every time it orbits, it's blocking just that little bit of light every time it passes through. So that's called the transit method. And then the radial velocity, the star is pulling the planet around, but the planet is equally pulling the star. According to Newton's laws, where reaction is an equal and opposite reaction, right? That is law number 3. So the star pulls on the planet pulls on the star, but the sun or the star is way more massive, so it's pulling on the planet a lot. It's pulling on the planet the same, but there's a bigger effect because the star has more mass. So, but the planet is pulling on the star, so it is causing the star to wobble a little bit. So even though the star is causing the planet to go around, the planet is causing the star to wobble a little bit. And if we look at that wobble, we can determine, excuse me, we can determine if there's a planet there, and the size of the planet, and a bunch of different information. All right, I think this is the last slide. I wanted to talk about the seasons of the Earth because a lot of people get this wrong, and it's something that I think every high school graduate should know. Why do we have seasons? Fall, winter, spring, summer. First off, all planets have an elliptical orbit. So the orbit is not, I can't make a circle. It's not completely round like a circle. It's actually more like an egg. It's oblong, it's elliptical. Okay, so the seasons are not due, the Earth's seasons are due to the tilt of the Earth, not the closeness to the sun. So here we have a picture. You can see it's not a circle. This side on the left and the right are farther away than the top and the bottom, so it's squished this way a little bit. So the top and the bottom, this is not summer. It's not summer because it's closest to the sun. The reason we have summer is because of the tilt of the Earth. So the Earth is not straight up and down like this. The axis, we're not spinning like this. We're actually spinning at about a 24 degree angle. So tilted 24 degrees. And so the reason there's a summer, over here we have the summer in the northern hemisphere, which is where the United States is at, because the United States is tilted towards the sun. And so because it's towards the sun, we're getting more sunlight. So right here, tilted toward the sun, we're getting more sunlight. And on this side, we're tilted away from the sun. And so because we're tilted away from the sun, there's less direct sunlight hitting us. And so it's winter. And then, of course, the top and the bottom, it's actually not hitting us. The tilt isn't affecting it because I mean, you can just see if the sun is here, this tilt, the sun is tilting toward it. But if I put it here, it's tilting this way, but the sun's lights are coming this way. And so the tilt isn't affecting the light. And so that's what when we have our fall and our spring is here. And then, of course, the seasons are opposite in the southern hemisphere. So during our summer, when we're tilted toward the sun, the southern hemisphere, like Argentina or Australia, are tilted away from the sun. So it is their winter in June and July. And it's their summer in the opposite time. Because right here, you can see Australia will be pointing towards the sun. So it'd be their summer in December. All right. And that is the end. Please let me know if you have any questions. Please fill out the survey. There's still not people answering the survey, and you're losing such easy points. So please do that and complete the solar system problems. And we will have a test next week on this whole unit on astrophysics. So we will have a chance to review. There'll be some review problems, and kind of like I always do, and then we'll have a test by the end of the week. So thank you guys. I will chat with you next week, or stop by during any of the Zoom sessions or office hours, and we can talk. All right. Thanks, guys. Have a great week.